Okay, so for the Calculus 1 class, let's do a problem using integration, and let's solve a real-world problem, and let's see how this works, okay? So the problem that we have here, okay, is that I have a generator running, all right? And that generator is producing AC electricity, okay? Now, the problem is that I want to convert this alternating current electricity. You can Google this stuff. I want to convert this to direct current, okay? I want to make it into a direct current. In other words, a direct current graph where this would be my voltage, okay? A direct current graph would look like this, all right? So my question is, this thing has a certain amount of power in it, okay? And I happen to know that power in this wave is basically the area under the wave, okay? So this area here, all right, represents the power that this wave holds. And here, this also represents power. So the question is, how much direct current power can I get out of an alternating current waveform? That's a very practical question, okay? So, basically, what we want to know is what voltage here will give me an equal area under a straight line compared to this sine wave, okay? Now, we talked about integration being an area, right? So let's integrate this and let's see what we get, okay? For right now, we can just go ahead and let this be 1, okay? And so this will be some number, apparently less than 1, right? Okay, so this integral has got to have a left boundary, right? A vertical line. This is the line x equals 0, okay? So the left boundary goes here. So that's my vertical line, right? Now we know from the unit circle, right, that sine is going to complete half a cycle in pi, right? So this is going to be pi, completes a full cycle in 2 pi, where we're using this axis in radians, okay? Or arc lengths, right? Okay, so here we have the other vertical boundary, right? And that's going to be x equals pi, vertical line. Okay. So our upper function here, I think it's pretty obvious that our upper function here is going to be sine x. And then we have to subtract our lower function, right? Now, our lower function is going to be this line right here. This line has an equation, the equation of a horizontal line, okay? This line is g of x equals 0. That is the x axis, okay? So this function right here is 0. Now, we're going to chop this into little vertical rectangles, right? Let's blow this up a little bit. So we have, this is the line x equals pi. This is the line x equals 0, right? This is the line y equals 0. And this curve is sine x. And this value here would be 1, okay? Okay, so we're going to have to chop this into vertical rectangles, right? We talked about that, right? How this integration process works. So we're going to chop it up into n rectangles, and then we're going to take the limit as n goes to infinity, all right? But basically, what we've got here is we've got this width, and that width is going to be b minus a, which would be pi minus 0, right? b minus a over n, okay? And we said that in the limit, as n approaches infinity, that this thing is going to be dx in our integral over here. Now, notice that we've got sine x minus 0. Now, all of these definite integrals, okay, have an upper function and a lower function. But many times, or I guess practically always, we don't need to show minus 0, because I mean, what's sine x minus 0? It's sine x, right? So this integral, you would typically see it written like this. Now, when they write an integral like that, they're assuming that you understand all of this other stuff, okay? They're assuming that you understand that this is the vertical line x equals 0. I'll typically just go ahead and put it, okay? They're assuming that you understand this is the right-hand boundary. They're assuming that you understand that the lower boundary of this area is the x-axis, because there's a 0 here. Okay, so all those assumptions are being made. Make sure that those assumptions are correct. In other words, that you actually do know those things. Okay? Because without that, this can look pretty confusing. Okay? Now, what do we do with this? Well, the first thing that we need to do is we need to do an antiderivative. Okay? So what does that mean? It means that this sine x, okay, is a derivative that somebody took. Somebody took the derivative of something, and that's what they got. They got sine x. Okay? So I think we know that they must have taken the derivative of cosine x, right? Because the derivative of cosine x is negative sine x. Okay, well there's a problem there, yeah? So we have to put a negative in front of here, okay? What's the derivative of negative cosine x? It would be negative sine x, yeah? Okay, and that would be positive sine x. So this is the first step, the antiderivative, okay? Then we're going to put a line here. This is the evaluated from here to there symbol, okay? Evaluated from x equals 0 to x equals pi. This evaluated from is really just two parentheses with a minus sign in the middle, okay? That's all we need to do. And then we need to copy this term into each of the parentheses. Now, make sure you copy it carefully, okay? There's a negative in front, right? So it's negative cosine blank, negative cosine blank. So why did I leave those things blank? Well, we're going to plug this top number in here, and we're going to plug this bottom number in here. Now, of course, we have to have a good name for this, okay? This is called the fundamental theorem of calculus. I know, really? Two parentheses with a minus sign in the middle? Fundamental theorem of calculus, okay? All right, so let's look at that. So we've got negative cosine pi minus negative. Well, minus negative is positive, right? Positive cosine of 0. So here we are again with the unit circle, right? If you don't know the unit circle, you should stop this video right now and go and memorize the unit circle, okay? And then you can come back and pick this up. Okay, so cosine pi is negative 1. So this is negative 1 plus cosine 0 is 1, okay? So this is 1 plus 1, so the answer is 2. Now, this might seem strange. This certainly seemed strange to me the first time I saw it. The area under here, this area is 2, okay? You would think that with that strange shape on the top that it would be some weird number, but it's not. It's 2. Okay, so what does that tell us? Well, this is pi, remember? This distance right here is pi. And what we want is, we want the height of this rectangle so that we can get the same area. Right? Okay. So I'll let that height be V. Yeah? Remember, that's our DC voltage, yes? So it's going to be pi, this is the width of our rectangle, V, that's the height of our rectangle, that's going to have to equal 2, right? This is not difficult to solve, yes? The voltage is actually 2 over pi. So if we have an alternating current waveform with a 1 volt peak yes? And we were able to convert this perfectly. We can't, there are going to be losses, there's efficiency in the conversion process, but if we could convert it perfectly, yes, the new voltage we would get would be 2 over pi. So here's a practical problem using integration, okay? If you have any questions about this thing, feel free to send me an email, or any other integrals that you run into, okay? Send me an email with the integral in it, and I'll make the video trying to help you out.